So we've been talking about light as electromagnetic radiation. Visible light is only a small part of the whole spectrum of electromagnetic radiation. The shorter wavelength light has a higher frequency and it has higher energy. A longer wavelength is a lower frequency and a lower energy. And I say that slowly because those relationships are so easy to get backwards. So let me just draw you a picture so that you know what I'm thinking as I'm saying those things. So I think of two waves. Okay, they're messy, but you get the idea. Which of those looks more energetic? The top one or the bottom one? The top one, right? So this is high energy, and this is low energy. This looks fast and that looks slow to us, but they're both moving at the same speed, okay? So this is the wavelength, this is the wavelength. Which is the longer wavelength? The one on the bottom. So this is larger wavelength, this is shorter wavelength. Short wavelength, high energy. Long wavelength, low energy. If you were standing, let's pretend they're moving to the right. If you were standing over here and both of those waves are moving at the same speed, which one's going to hit you more frequently? The top one. So the top one has higher frequency. So this is high frequency and this is low frequency. You think you can do that? Draw a picture and reason it out like that? That's the only way I remember it, and I'm the teacher, right? It works. Draw a picture, and you get your exam before you read any of the questions, because as soon as you read the first question, your mind goes blank, right? Have you had that happen? You know everything, and then you read the first question, it's all gone. Before you read the question, turn the exam over and draw your own crib notes that you brought in your brain on the exam. So draw this picture on the exam, and then you can easily answer questions about the relationships between these three quantities. So in this electromagnetic spectrum, we've got radio waves with the lowest energy. So low energy means those have a really long wavelength. Gamma rays are at the other end, they have the highest energy, so they're going to have the shortest wavelength and the highest frequency. Those higher energy forms of radiation can damage biological molecules. They are ionizing radiation, meaning the energy hits biological molecules and it has enough energy that it can actually ionize. It can add an electron or remove an electron from those molecules. That's going to change the chemical behavior of the molecule and cause all kinds of problems in that organism. Okay, so here is the electromagnetic spectrum. This is a very typical way to represent it. If you look online, you can find all kind of different representations. So one thing that seems to be really confusing to students is you misunderstand what this part down here means. This part is zooming in on that. So we've taken this and we've just expanded it so we can actually see it. So red light over here actually is here on this spectrum. So here's radio waves, microwaves, infrared. The visible is actually this little tiny part in the middle, ultraviolet, X-ray, and gamma. So please do not tell me that red light is lower in energy than microwaves. You look at the table, you look at this, and you see the red down here, and you're like, oh, it's down here in the radio. No, it isn't, it's up here. Okay, so don't misunderstand what this diagram is trying to show you. So I want you to read in your textbook about microwaves, infrared, visible light, ultraviolet, and X-rays. There are brief descriptions in your textbook. You can read that and understand it. It's nothing huge that I have to explain to you. One thing I want to point out to you is it can be hard to keep these types of radiation in the correct order. So use the use the visible light as an ordering principle. And what did we learn about the colors? How do we remember the order of the colors? Roy G. Biv, right? So here's red, orange, yellow, green, blue, indigo, violet, right? Left to right, just like we read, low energy to high energy. That's how we typically write number lines, as they're getting bigger to the right. So violet light is higher in energy, red light is lower in energy. So then you get into here, ultraviolet, ultra means more, right? Super. So ultraviolet is above violet. And what does ultraviolet light do to you? Gives you a sunburn, right? It's got lots of energy. So this is the high energy end. Infrared is below red. So that's on the other side of the red. X-rays and gamma rays. X-rays are used pretty commonly to, image your teeth and your bones, etc. They can cause harm to you, but in small doses, they're fine. Gamma rays, that's the dangerous, scary stuff. So this is higher energy. And then down here, we've got microwaves and radio waves. Do radio waves do anything to you? No, there's radio waves floating all over the place. If you get out a transistor radio, you can tune it to lots of different stations, the car radio. The radio waves are everywhere, and they're not affecting us at all because they're so low energy. Microwaves, that one's a little hard to get your mind around because you're like, but microwaves make my food hot. If you're curious about that, I'll explain it to you during lab. So we can separate a continuous spectrum like white light by wavelength. So this prism separates the white light into a continuous rainbow. Oh, I forgot about that picture. One of the things that can be done with infrared light. So infrared light is So infrared light, we can't see it with our eyes. It is the electromagnetic radiation that comes off of things that are warm. I think I'm emitting quite a bit of infrared light right now. So we can't see it with our eyes, but we can build detectors that can detect it. And this is where night vision comes in. Thermal imaging. So you can get a camera that is sensitive not to visible light, but to infrared light. And this is a picture I took at the JPL, NASA's Jet Propulsion Laboratory. My daughter got to go on a field trip, and I was able to go along with her. And they had this cool setup here where they had this video camera, and you could see yourself with visible light and with infrared light. And so I took a picture because I just thought that was really, really neat. And as you can see, our skin is warm, our clothing is cooler, and then the background is cooler yet. They choose what colors to represent that in, when they design the computer software to do that imaging. But infrared light, thermal imaging can be used to find warm things in the dark. So completely dark room, you could find a person because they're going to be warmer than the surroundings. Kind of cool. Really high energy radiation, like gamma rays, can be used to kill cancer cells. So cancer cells are bad, but we want to preserve the healthy tissue around the cancer cells. So there are brain tumors that you can't operate on, because if you cut into the brain to remove the tumor, you do more damage with the surgery than the tumor's doing. And so that's a big problem. But there's a technique called gamma knife. And so what they do is they take the radiation and they target the tumor from multiple directions. And so each of these beams is going to do a little bit of damage to the healthy tissue that it goes through, but it's also going to damage the tumor. But the tumor is getting hit from all of the beams. The healthy tissue is only getting one beam. So you get a little bit of damage to the healthy tissue, but a lot of damage to the tumor. And so that's using high energy radiation for good things. So electromagnetic radiation is a wave, and waves can interact with each other. So the interaction can be constructive or it can be destructive, and we call it interference. So constructive interference happens when you have two waves that are in phase, meaning their crests line up and their troughs line up. So when these interact, they will add to each other and the amplitude becomes larger. When you have two waves that are out of phase, so they're here, the crest of one is lined up with the peak, with the trough of the other, then they will cancel out, and that's destructive interference. This is one of the things that happens on a trampoline if you've got two people jumping. If you do it just right, you can get sent really soaring high, and if you do it the other way, it's like you jumped but nothing happened, right? Because the interference can either enforce or counteract your bouncing motion. So that's a characteristic of waves. Another characteristic of waves is diffraction. So when a wave encounters a barrier or an opening in a barrier that is similar in size to the wavelength, it can travel around it, but when it does that, it bends. So this is something that waves do. Traveling particles do not diffract. Particles act like baseballs. If they hit the wall, they bounce back. If you throw them through the door, they just go through the door. Throwing a baseball through the door does not cause it to bend and go around the corner. But a wave going through a doorway would bend and go out in different directions. So diffraction of light through two slits where that distance is comparable to the wavelength. So the distance between the slits has to be similar to the wavelength. That can result in an interference pattern. So you have the two waves going through the slits, and as they diffract, they begin to interfere with each other. And that interference pattern happens with all light waves. So what on earth am I talking about? So diagrams. So here we have waves, and we're using these lines to represent the crest of the wave. So here's up, and it goes down, and it comes back up, etc. So as the wave comes to this barrier that has a slit in it, it doesn't just stop. As the wave travels through this slit, it diffracts, and it's now curved. And you can observe this with waves on water. This happens. When particles encounter a slit, if they hit the barrier, they bounce back or they stop. If they hit the slit, they just go straight through. Okay? So waves and particles behave differently when they encounter a slit in a barrier. So if we have two slits, this is a somewhat famous double slit experiment. So here we have a single light source. So the radiation coming from this light source will be in phase because it's coming from the same place. So it's in phase and it's spreading out in all directions because that's what lights do, right? You have a light bulb, it doesn't just give off light in one direction. The light goes all around. So we're just looking at a segment of it. So this light, these light waves travel, and as they hit the slit, when waves hit a slit, they diffract. So it hits the slit here, and it curves and keeps going, and it hits the slit here, and it curves and keeps going. The diffracted waves on the other side of the slit are also in phase with each other. And as they travel out, this crest and this crest will run into each other at some point, and they'll cause positive or constructive interference. And other places, the crest of one will run into the trough of the other, and they'll cause destructive interference. And so if we put a piece of film and allow the light coming through those slits to shine on the film, what we see is a pattern of light and dark bars. And this is from the interference of those diffracted light waves. So here's, my pointer's acting up. Here's waves out of phase. Come on, pointer. There. Waves out of phase. You add those together, you get a straight line. And so that's where you get a dark spot, because the light cancels itself out. Is that trippy? That's trippy, right? And here, the light reinforces itself and gets brighter. So we've got bright spots and dark spots. This can happen with sound waves too. You've heard of noise-canceling headphones. How do those work? Well, the technology inside of them takes the sound waves and shifts them just a smidge and combines them again with the sound waves coming in unshifted, and so it causes this destructive interference and basically cancels noise. Pretty neat. Okay, so you've had an introduction. Now we're going to watch this video, and then I'll explain it to you again, and hopefully it'll make sense the second time. And get the computer to cooperate. Come on. There we go.
What is light?
What is light? What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The color.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box.
Two bright bands.
Two little lines.
Yeah, I think it'll be one line instead of two.
I can expect the whole box lit up.
That can be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored. The one in the middle is just white.
Kind of a rainbow.
The rainbow color as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. How does this make any sense?
There's some kind of principle involved there. The average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern.
See that?
This pattern is created by the ripples in the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere, and you wouldn't see any light there. It's light canceling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same
And then they go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, and then a bright spot.
Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah,
that's because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So
between
there's
red
still
and blue,
that red bin over there, the green part, I'm seeing
It's a
that
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened. Literally.
So that's one of my favorite YouTube videos. Now hopefully this diagram makes a little more sense. Whoops. So the ripples, the waves coming through, going through the two slits, this is what he was recreating with the two balls going up and down. The two sources of ripples, of waves, in phase with each other and spreading out. When light comes to these slits, it causes that, and as these interact with each other, we get these different patterns of bright and dark light. Does anybody have any questions? Yeah? Okay, so what was going on with the color? So with white light from the sun, the light coming in here does not all have the same wavelength. It's a mixture of different wavelengths. It's all the colors together. And so as the light hits here and begins to spread out, this pattern here is based on how far apart the wavelengths are. So if the wavelengths are different, the pattern is going to be different. So the red light is bent differently than the blue light, and so they're going to overlap in bright and dark places at different points on the screen. So in the middle, we saw the really bright white circles. And then as it went off to the side, they got dimmer and they became more single colors. That's because now we're not getting all the light reinforcing itself in the same point. The red light is making a bright patch in a different place than the blue light. Does that make sense? If you use light of one frequency, then you would get a regular pattern like this. That's a good question. Anybody else? So that's what waves do. The photoelectric effect is the observation that many metals will emit electrons when a light shines on their surface. So classic wave theory says, well, this is the light energy being transferred to the electrons. And if that's true, then only the intensity, the amplitude of the light would affect the emission of electrons, because the intensity is the brightness, right? So the idea is that if a dim light was used, there'd be a lag time. So you shine the dim light on the metal, and you'd have to wait a while for the electrons to absorb enough energy from the light. Whereas if you used a bright light, you'd get electrons coming off immediately. Does that make sense? At least to one person, so that's good. So this is the setup here. So light hits a metal surface and electrons are emitted. Now that's not something that you can just detect going on anywhere because electrons are really small, right? So we do it in an evacuated chamber, and we put a positive electric field here and a negative electric field on the metal. And normally electricity is not conducted through nothing, right? It doesn't go through air very well. It goes through a vacuum even less well. It just doesn't go. There needs to be something to move. Electric current is a flow of electrons. So the light hitting the metal in this evacuated chamber, if it emits an electron, if it spits an electron out, the electron will travel over to this positive terminal, connecting the circuit, closing the circuit at least for a brief moment, and we can read current on that, on the meter. If there's no electrons being emitted, then there'll be no current. So we can monitor whether electrons are being ejected or not. So this is what was found experimentally. So this graph is showing us the rate of electron ejection. So down here is no electrons being ejected, and up here's a lot of electrons being ejected as a function of the frequency of light. So this wave idea said, well, a dim light will give us, will still give us current here, electrons being ejected, but it's just going to take a while. What they observed is, at these low frequencies, it didn't matter how long you shone the light. There was never any electric current. There were no electrons being ejected. When you got to this frequency, all of a sudden, you got a lot of electrons being ejected. If you went higher than that, there's a little bit of curving here, but it quickly gets to a maximum, and it doesn't matter how long you shine the light on that piece of metal, the current will be the same number of electrons being emitted per second. If you use dim light, you get a lower level here. If you use a higher intensity light, you get more electrons. But there's this magic frequency. Lower than that frequency, no electrons ejected. Above that, lots and lots. So that's called a threshold frequency. And there was no lag time. So the higher frequency light, you hit the metal with it, electrons are ejected immediately. And the low frequency, doesn't matter how long, nothing comes. So this didn't work with this wave theory of light. So Einstein had an explanation for this. He proposed that light energy was delivered to the atoms in packets. So basically, he's saying that light is a stream of particles. So these particles or packets are called quantums or photons. You've probably heard of photons. Fire the photon torpedoes, right? Photons. A photon is a piece of light. The energy of the photon is proportional to its frequency. And then it's inversely proportional to its wavelength. So the energy of this photon is equal to a constant times its frequency, or a constant divided by the wavelength. So that constant is called Planck's constant. It's given the symbol lowercase h, and it's 6.626 times 10 to the minus 30 joule seconds. Now that's a number that you do not need to memorize. I'll give that constant to you, because we don't use it a lot, and I have a hard time remembering it. But that's Planck's constant. So this is Einstein's explanation. So what does this mean then? Well, it means that as the light is hitting that metal surface, it's essentially a stream of particles, and each particle has a certain amount of energy. And so if the particle hits the metal and it doesn't have enough energy to remove an electron, nothing happens. And it doesn't matter how many particles hit, nothing happens. But if the particle has enough energy to emit the electron, it will do so. And it doesn't matter once you get past that threshold. Okay, so it's a little bit like, you've seen dunk tanks, right? Where you've got like the principal sitting on this platform and you pay money to throw baseballs at the little target. So if you hit the target but you don't hit it hard enough, what happens? Nothing, right? If you throw the baseball and you hit it hard enough, down goes the principal, gets all wet. What if you throw the baseball twice as hard? Does the principal get twice as wet? No, it's either enough or not enough. And so that's how it is with this. So let's do this problem here, dealing with the energy of photons. So a 100 watt light bulb radiates energy at a rate of 100 joules per second. The watt is a unit of power, which is energy over time, and a watt is 1 joule per second. So if all of the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? And let's just assume 3 sig figs. So what's the answer? What the heck, right? Okay, let's pick this apart. We can do this. We'll pull the numbers out and see what we can do with those. 100 watt light bulb, 100 joules per second, and then this little parenthetical statement here. We don't need to use the 100 watts, we're going to use the 100 joules per second. So 100 joules per second, and we're given the wavelength is 525 nanometers. So joule is a unit of energy, right? And we had that relationship, the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. So we want to know how many photons in 1 second. So I'm going to start working on a path up here at the top. So we're starting out with the time of 1 second, and we want to get to number of photons. And it's kind of a big mystery what's in the middle here, right? Well, 1 second, we've got this relationship that there's 100 joules per second. It's radiating energy at a rate of 100 joules per second. So could we figure out how many joules are being emitted in 1 second? Well, sure, it's 100, right? So we could convert seconds into joules, because we have that power relationship there. Well, that's an amount of energy. Could we figure out how much energy one photon has? Could we calculate that from the wavelength? Yeah, we could. We haven't done it before, but we can do it. If we knew the energy of one photon and we had this amount of energy, could we figure out how many photons were giving that much energy? Yeah. So there's this big long gap here, but it's really only 2 steps. Always leave plenty of room because, you know, I didn't know it was just 2 steps. I just started. Okay, so we need to calculate the energy of a photon because that's our conversion factor here. The conversion factor here is the power, 100 joules per second. Okay, so the energy of a photon equals H. Well, what's H? It's on the previous slide. I believe it's 6.626 times 10 to the minus 34 joule seconds. Yeah, nailed it. So that's Planck's constant. It's a constant. It's always going to be the same. So we've got that, and we need to multiply that by the speed of light. And if you don't remember what it is, you go look it up. It's 3.00 times 10 to the 8th meters per second. Look, the seconds are going to cancel out. And we're going to divide this by lambda, the wavelength. So 525 nanometers. The units help us out. So here I've got meter and I've got nanometer. Those are not going to cancel, are they? I have a meter up here. I want meters down here. So nano means 10 times 10 to the minus 9. So I can do this conversion just by writing the numerical meaning of nano. Nano means times 10 to the minus 9 meters. Or you can take 525 nanometers and set up a separate equation and do the calculation. Not proper scientific notation. Your calculator doesn't care. So now meters cancel out and we're left with the unit of joule, and that is the energy of one photon. So 6.626 EE minus 34 times 3 EE8 divided by 525 EE minus 9. We're assuming 3 sig figs, it says. So 3.7862 times 10 to the minus 19 joules. That's the energy of one photon of light, one piece of light at this wavelength. Any questions about that? Okay, so that's the amount of energy equal to one photon. So now I have the pieces that I need. I'm going to take 1 second, and I'm going to multiply by joules and divide by seconds. And then I'm going to multiply by photon and divide by joule. Dimensional analysis, getting the units to work out. So we're told that this light bulb is giving off 100 joules per second. So 100 joules for every 1 second. We just calculated that the energy of each photon is this 3.7862 times 10 to the minus 19 joules. So I'm going to write that number here in the denominator. 3.7862 times 10 to the minus 19. And that will be for one photon. So I've got 1 times 100 divided by that energy, and I get 2.64 times 10 to the 20. Photons. Is that a reasonable answer? What do you think? Are photons, are pieces of light big things or small things? They gotta be super small, right? So if we've got this light bulb radiating energy, it can't be giving off just a couple of photons. Could it give off less than one photon? No. So if you ended up with times 10 to the minus 20, right? Something went wrong in your calculations. It's like an atom. You can't have part of an atom. You can have a photon, you can have lots of photons, but if you don't have one photon, then you have none. They're pieces. Any questions? Okay, so here's one of those arranging orders. So green, red, and blue. Arrange these three colors of visible light in order of increasing wavelength, frequency, and energy per photon. So apparently, they don't teach this very well in school. What does it mean to put something in order of increasing? Smallest to largest. Okay, I always thought that was obvious, but apparently it's not, because I get a lot of people who put it exactly backwards. So I just want to be clear. Order of increasing means you start with the small and it increases as you go down the list. Okay, so we're looking for the small one first and the large one last. So how do we do this? So the way I would answer this is I would draw myself a little picture. So I'm going to draw a little ugly picture here. So I've got Roy G. Biv, right? The colors of the rainbow, and so that's my visible light. And then I had this electromagnetic spectrum, right? What was next to violet? Ultraviolet, right? So UV. And what was next to red? Infrared, or IR. So that's not too hard, right? So which gives you a sunburn, UV or infrared light? UV. So this is high energy. So this end is high energy, and this end is low energy. So we could do this one right now. Energy per photon. Red, green, and blue. So we've got red, green, and blue. We want to do order of increasing. We'll start with the lowest energy. Which one has the lowest energy? Red. So it's red. And then what's next? Green and blue. Right? Because this is lowest, this is highest, so it goes red, green, blue. Okay, so that's that one. But we also need to do wavelength and frequency. So now I'm going to draw myself another picture. Big slow wave and bouncy wave. I think of this as somebody jumping up and down slowly, and this is somebody going nuts. Right? Lots of energy. This is high energy. So that's high energy. This is low energy. So here we've got the bouncy one, and here I've got the slow one. So is this longer wavelength or shorter wavelength compared to this one? This is long wavelength. This is short wavelength. So order of increasing wavelength, we want to put the one with the short wavelength first. Is it red, green, or blue? It's blue, right? I know, it'll just twist your brain in circles and knots. Short wavelength. It's a short distance. So this is the shortest wavelength, and the wavelengths get longer as you go the other way. So we've got blue, and we're going to the left this time, and then green, and then red. Sometimes you'll see this instead of commas, you'll see greater than or equal, greater than or less than. So blue is less than green, green is less than red. And You know, we don't use those symbols a lot in everyday life, and so some people tend to forget which one is which. So this symbol, this end is small and pointy, right? And this end is big and wide. Hey, this is, so small and pointy, this is the small one, and the big end of the symbol is the bigger one. Okay, so let's just all be real clear on that. Okay, so frequency. If I'm standing here and these waves are coming at me at the same speed, which one's higher frequency? Hits me more frequently. The one on top, right? So that's this one over here. It's the one with the higher energy. So that's more frequent. This is more frequent. So I want to put that at the big end. And that means that this one is less frequent, lower frequency. So the red goes over here, and green is in the middle again. Green's always going to be in the middle of this. Any questions? Yes? The wavelength, yes. I can explain the wavelength one again. Okay, so I drew these two pictures. Wavelength is the distance between adjacent peaks, right? So this one has a long wavelength, right? This is a bigger distance, and this is a shorter distance. I put this one over here with high energy because when I look at that, I think of someone jumping up and down with a lot of energy. This just looks more energetic. Now that's not a scientific way of doing this, but it works. So who cares how you get there, right? So this is more energetic, so I put it up here. That's higher energy, short wavelength. Down here, this one looks low in energy, and this has a long wavelength. Okay? Anybody else? There are some things that you just flat out memorize, and this is something that can be memorized, but good grief, it's so confusing because there's the ups, the bigger and the smaller, and they're just all tangled up. So the only way I can remember this is to make pictures like this. So I have taken what I do in my head and I put it on the PowerPoint slide for you. And I would recommend just learning how to think about it, because if you can remember just some big ideas, then you can reason out whatever you need on the exam question. Okay, so back to those electrons being ejected. So one photon at that threshold frequency has just enough energy to kick out an electron. The amount of energy needed is called the binding energy. And I'm blanking. Is that phi or psi? Anybody know? Phi? It's a Greek letter. It's a weird Greek letter. That guy. We're not going to have to use him very much. It's what? Do you know what it is? No?
Epsilon.
What do you say?
Epsilon.
Epsilon? Okay. I believe that. I can't remember. So epsilon's the binding energy of the electron. If you irradiate the metal with higher frequency photons, the electron is going to absorb all the energy of the photon. It's going to have enough to escape the binding energy, and it's going to have extra energy. So the principle in the dunk tank, I don't know where that one analogy came from. Now I remember the better analogy. It's a kid going to Disneyland, right? That sounds fun. So the binding energy is the admission price. So let's just say it's $100. So you go to Disneyland and you have $95. Are they going to let you in? Nope. If you have $50? Nope. If you have $99, are they going to let you in? Nope. If you have $100, will they let you in? Yes, because that's the price of admission. That's the binding energy. If the photon has just enough energy to pay the cost, the electron can come out. What if it's more? What if you go and you have $250? Will they let you in? Sure they will. They'll take your $100 and you get to keep the $150, what you had above. And then what do you do with that? Well, you spend it, of course, right? You buy food, you buy like a hamburger, right? And there's your $250. It's gone. I don't go to Disneyland very often for that reason. Can you imagine taking 6 children to Disneyland, right? And then if you're going to stay overnight, they make you get 2 hotel rooms. This is, no, they can go in high school when the choir takes them. Yeah. Poor Andrew. He's 9. He's never been to Disneyland. I know, right? Shh. He doesn't know. Don't tell him, please. Anyway, so the excess energy, if a photon comes in with $250, $100 goes to breaking out the electron, and the other $150 is just energy that it gets to take with it, and it does that as kinetic energy. Okay? So the electron coming out will have a different amount of kinetic energy based on how much energy the photon had. But the number of electrons coming out is going to be the same regardless, as long as you have that minimum. So the kinetic energy of the ejected electrons is the energy of the photon minus the binding energy. So the energy of the photon minus the binding energy. So this is the amount of money that you have going to Disneyland. You subtract the amount you need to get in, and that's what you have to spend. That's kinetic energy. And so we can express this as h nu minus epsilon. Okay, suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? Well, we need to know the relative energies of yellow light and ultraviolet, right? So Roy G. Biv, next to violet is UV, and over here is IR. This is high energy, because that gives me a sunburn. I can get a sunburn just going out and peeking at the sun. So here's the UV, and we're looking at yellow. So yellow light has lower energy than ultraviolet. So yellow light will eject electrons. So a kid with yellow light has enough money to get into Disneyland. Ultraviolet has more energy. Kid with ultraviolet has more than enough money to get into Disneyland. Does that make sense? So with the ultraviolet, no electrons would be ejected? That's not true. It's got more energy. They'll definitely be ejected. Electrons would be ejected. They're going to have the same kinetic energy as those ejected by yellow. So the ultraviolet with more money, he has the same amount of money to spend once he gets in as the yellow. No, he's got more, right? So that's not going to work. Electrons would be ejected, and they would have greater kinetic energy than those ejected by the yellow light. Yep, that sounds like our winner. Always read the last one, though. Electrons would be ejected, and they would have lower kinetic energy than those ejected by yellow. No. Does that make sense? So this is where we get to that superposition idea. The wave-particle duality of light. Light can behave as a wave, or it can behave as a particle. And actually, when we're not observing it, it's both. It's a particle and a wave. When we observe it, we force it to behave like one or the other. So which behavior you observe depends on the specific experiment. But it is a light and it is a wave and a particle. So let's just back up here real quick. Try to reinforce an idea. So with this photoelectric effect. Is light behaving like a wave or a particle here? It's behaving like a particle. So the photons of light are striking, and if that one photon has enough energy, it can kick out an electron. If it doesn't have enough energy, nothing happens. It's not that it builds up. So here, light is behaving as a particle. Back here, is light behaving like a particle? No, it's behaving like a wave. Particles can't interfere with each other and cause interference patterns like that. So that's the experiment that shows that light behaves like a wave. So it depends on how you observe it, how it behaves. Because actually, it's both. And that should be disturbing to you. It's disturbing to me. Doesn't seem possible.